Hello everyone, this is Ayush and I am here to solve this question for you guys. So basically, whenever you are trying to solve a question, the first approach should be to gain all the information from that question and dissect that question so that you basically know what the question is trying to ask for, and you have all the hidden information or whatever is given, that so that do not miss out anything in the calculation part, right? So this question basically is about a proposed space station that consists of a circular tube that rotates around its center, and it has a diameter of 1.1 kilometer. That is the first information. And so it is asking what will be the revolution speed if we want to produce an effect of 0.9 g at the surface of the space station, where g is the acceleration due to gravity at the surface of Earth, right? So now we know what we have to do is, when the space station will revolve, if any object is kept on the surface of the space station, it will the net forces will act on it in such a way that it will have a centripetal acceleration towards the center, right? And we want that centripetal acceleration to be 0.9 g, so that the effect, which is basically what this question is asking for, the effect, the effect should be 0.9 g, which basically means the centripetal acceleration should be 0.9 g. And we have all other information too, like the diameter and every other thing. So we have to just do a simple step. We have to equate the centripetal acceleration of this object, any given object, to 0.9 g, right? So first what we'll do is, we will do all the calculations in SI unit, because this question is asking for the revolution frequency, or whatever you can say, in revolutions per day, right? So which is not an SI unit. Calculations that way become really tough, like this is in kilometers, that is in revolutions per day. So what we'll do is, we'll have a basic standard system. We will do all the calculations in SI unit, and then we will change in the end accordingly. Okay, so let's get started with the calculation part. So basically, first what we'll do is, we'll find the radius. The radius will be 1.1 into 1000 divided by 2, that is 550 meters. Why 1000? Because it is given in kilometers and we want to find it in meters, right? So the next step is very simple. We do not have to do anything. We just have to equate the centripetal acceleration with 0.9 g. Okay, centripetal acceleration, as we all know, is v square by r, or you can say omega square r. Both of them are same. This is the formula for centripetal acceleration, right? I'll highlight it for you guys. This is centripetal acceleration. Omega square r, this formula can be derived from this one, as v is equal to omega r. So we get this formula, right? So what we have to do is, we will equate omega square r with 0.9 g, because we want to find omega, right? Because the angular velocity is directly related with the revolutions per second, right? So it will be convenient for us to directly find angular velocity rather than finding the velocity. Anyway, you can proceed with any of the methods. Both of them are going to lead you to the same result, but we are doing with this one as it will be a shorter and concise method, right? So basically what we have to do is, omega square into 550, which is the radius, 550 meters, is equal to 0.9 into 9.8 meter per second square, which is the value of acceleration due to gravity at the surface of Earth. So meter and meter. So basically we can verify from here that we are going to get omega in the units of second inverse, which is exactly the units of omega or angular velocity, right? Because angular velocity is the angle covered in a certain time. Angle will be in radian per unit time, as radian does not have any dimension, so the correct unit is second inverse, right? So basically just the calculation part now. 0.9 into 980 oh 0.9 into 9.8 divided by 550. This is our omega square. Now we have to solve for omega. And now we get omega with a very simple calculation. Omega is 0.127 radians per second. Now we do not have to do anything. We know that omega is equal to 2 pi into frequency, because angular velocity is the angle covered in certain time. We do not want to know about the angle, we want to know about the number of revolutions. And as angle covered in entire revolution is 2 pi, so dividing omega by 2 pi gives us the number of revolutions per second. So now we are going to solve it. 0.127 divided by 2 into 3.14, which gives us the frequency. So the frequency is equal to 0.02 revolutions per second. Very simple. Now we just have to convert this revolution per second into revolutions per day, because it is the SI unit and it asked and the answer was supposed to be given in revolutions per day. The conversion factor is very simple. Each day has 24 hours, each hour has 60 minutes, and each minute has 60 seconds. Very simple. So we'll multiply all of this and we'll come out to our final answer, 1751.01 revolutions per day. This is our final answer, guys. I suppose I made it very clear. So this is the basic gist of my solution, that solve everything in SI units and then convert it as per your needs. Like I solved it throughout in SI units, like I got the answer in revolutions per second, right? See, I got the answer in revolutions per second till all this was done in SI units, and then in the end I used the conversion factor and converted revolution per second into revolution per day, right? So this is our answer. And if the space station makes 1751 revolutions in a day consistently, then an effect of 0.9 g will be felt at the surface, where g is the acceleration due to gravity at surface of Earth, or we can say an effect comparable to Earth will be felt at the surface of space station. Thank you very much for watching. Have a good day. Bye bye.